Rotational kinetic energy is one of the most confusing topics in AP Physics 1, especially when rolling motion is involved. In this video, we'll break it down step by step. You'll learn what rotational kinetic energy actually is, how it compares to translational kinetic energy, the exact formulas you must memorize for AP Physics 1, how rolling objects have both types of kinetic energy, and how to solve hard AP level problems using energy conservation. So, by the end of this video, you'll understand the formulas, the intuition, and how to solve the hardest exam style problems. Now let's start off with some definitions. So these are the formulas that you must know. So what is translational kinetic energy? So this is energy due to motion of the center of mass. So this is K trans, which is subscript, is equal to 1/2 mv squared. This is a formula that you know already from earlier units. Now let's talk about a new concept, rotational kinetic energy. So this is energy due to spinning around an axis. And this is represented as K rotational is equal to 1/2 I angular velocity squared. So what you can see are some things in these two equations are analogous. We can see mass is analogous to angular velocity, and we can see mass is analogous to inertia, and we can see that velocity is analogous to angular velocity. So these are the two counterparts of each other, and you just have to know those variables so that you can interchange them with each other. So again, this is to re-emphasize that's moment of inertia, and that W is just angular velocity. And remember, moment of inertia is the same as mass in translation. So now let's talk about total kinetic energy. So what we need to know is that objects can have both at the same time. And what does that mean? So we know that the K total is equal to the sum of both of these. So that's 1/2 mv squared plus 1/2 I w squared. So that's just K translational plus K rotational. So remember, the total kinetic energy is both of these. You have to add up both the translational and the rotational kinetic energy. Now let's talk about the rolling without slipping condition. This is something that you need to memorize. So now let's say that if an object rolls without slipping, then we have the relationship that velocity is equal to the angular velocity times r. So this connects translation and rotation to rotation. So this comes up a lot in these problems. So now, the main difference is we can create a little comparison here. Rolling object. What is a rolling object? A rolling object, okay, more of just like analyzing what a rolling object is. So a rolling object, it moves forward, and it also spins at the same time. So when we think about this, let's say we have like a ball like this, and then let's say the ball is like this. It's like when the ball moves in a circle, let's say we mark this area of the ball like this. It's a sector, right? And then the sector, when it's moving, it not only rotates, but it also moves on the ground. So let's imagine that that's paint, right? And then when it rolls on the ground, it's going to leave behind a mark on the ground, and that's going to be a linear distance. And essentially, they're related to each other, so like the angle will also tell you like the linear distance that it travels. So you can kind of just like relate that into each other. So something we should need to know that is the energy, it will split into two things. It splits into translational kinetic energy. Again, this is center of mass motion. And then it also splits into rotational kinetic energy, which is spinning. When it's spinning around its center, when it's spinning around the axis of rotation, not the center. Remember, this is center of mass, and then this is axis of rotation. So that is the difference. Now, an important idea that you need to know is that the more energy that goes into rotation, actually the less translational speed the object has. Why? Because remember, it's the sum. So again, remember that it's the sum. So if you increase one, the other one has to be like increase, decrease. So remember, like, they're kind of like, it sums up to one thing, right? So that means that if you adjust one of them, the other one has to match, like, adjustment wise. So, and like this idea right here, the more energy that goes into rotation, the less translational speed the object has. Well, this is why different shapes roll at different speeds. So like, think about different objects that you have. Like, when you have more energy that's like rotating, that means the less translational speed it has. So like, if you have something that's rotating at a larger angle, it's gonna move slower when it's like, because it has to travel a larger angle. If it has to travel a larger angle, it has to move a less of a distance. So now let's do a practice problem to really understand these ideas. So we have a solid cylinder of mass m and a radius r that rolls without slipping down a ramp of height h. Find its speed at the bottom. So let's draw this out. Let's say we have this triangle right here, and then the cylinder, we're just going to represent it like this. I mean, you could represent it like 3D as well, like this. Right? It's going down at a velocity. So we want to find the speed at the bottom. And what is that going to be? What is that going to be? So we know we can use energy conservation with this problem. And when we use energy conservation, we define the initial and the final energy. So that means we have E initial is equal to mgh, right? And then we have E final is going to be equal to 1/2 mv squared plus 1/2 inertia times angular velocity squared. And this is because up here, the energy initially is going to be all potential energy, right? And then down here, we know that the energy in final form is going to be all kinetic energy, and we know kinetic energy is just equal to 1/2 mv squared. But remember, here we're examining rotational because it's rotating, right? Because when it went down, it went through the process of rotation. Because how did the cylinder go down? It rotated around its axis of rotation. And the axis of rotation is this. So instead of having its translational form, which we had up at the top, now we have its rotational form at the bottom. And we're not going to use that. We're going to use 1/2 inertia squared, which is why we did that. And remember that for the solid cylinder moment of inertia, the formula you need to memorize for that is going to be I is equal to 1/2 mr squared for a solid cylinder. And also we need to remember our rolling condition. So again, we have the rolling condition is equal to omega, which is angular velocity is equal to v over r, translational velocity, over the radius. So now we can just substitute this in. We're gonna make this, let's just make this blue, right? And then let's make this blue here. Actually, let's just color some things so that it's easier for us to keep track. E initial, the initial is just potential energy. Yeah, it's okay. So this EF is going to equal to 1/2 mv squared plus 1/2 right there. And then instead of the I, let's make this here. So the inertia again was up here, 1/2 mr squared times the angular velocity, which is the rolling condition, which is VR, and then this is going to be squared. Now, just doing some simple algebra, we have, well, what we can do is the E final, that's going to be equal to, let's move this here. We know that E final is equal to E initial, right? So that means that was all the E final. Let's move this over here to make this look a little neater. We know that was all the E final, right? So that means the initial was just potential energy, right? That was a potential energy. Okay, so this is just all going to be equal to 1/2 mv squared plus 1/4 mv squared, because you just multiply these two together. 2 times 2 is 4. And you distribute, okay. Yeah, and also we see that the r squared cancels out with this r squared, because when that distributes down there, and then you're just left with the v squared. So that's where you get this new expression, and now we can rewrite this as mgh is going to be equal to 3/4 mv squared. And if you're wondering where we get this from, you just add these two fractions, and that's just that. So now you solve for just v, right? You just want to get v, so then you have to reciprocal this by 3/4. And you also have to multiply, oh, we can see that m actually canceled out, so we don't need that anymore. And then you just take the square root of both sides, right? Because you want to cancel out, make this a little clear. You want the root of both sides. So that means you cancel out that, and then you just get that v is just going to be equal to the square root of 4 times gh over 3. And that is going to be your final expression. So now let's say we have problem 2. A solid sphere and a hollow disc roll down identical ramps from the same height. Which reaches the bottom first? So let's draw this out. We have the ramp, right? Well, this is not like a perfect ramp, but like you can see this as a ramp. Now we have this solid sphere. So this is going to be like a circle, right? No, this is gonna be like that, and then we have the hollow ring. So the hollow ring is gonna be like this. The ring is like this. So, and they're gonna both go down with the velocity of v. So we have this formula that we can use. We have v is equal to the root of 2gh divided by 1 plus c, and we know that the I is going to equal to cmr squared. And we also have these constants. We know that for the solid sphere, we have that c is equal to 2/5. And we know that for the hollow ring, that is c is equal to 1. And therefore we can conclude that smaller c is equal to, will result in a larger velocity. So from this we can deduce that solid sphere reaches bottom first. And this is because the mass cancels. So therefore the shape matters over the weight. So now let's do a third problem. Let's say we have a torque spins from rest to angular speed, angular velocity. Find the rotational kinetic energy gained. So we can use the rotational kinetic energy formula, which is K rotational is equal to 1/2 inertia times angular velocity squared. So now we know that if torque does work, right? Then we know that work is going to equal to the delta K of rotational, right? So that means this mirrors linear work energy. So this is translational work energy. We'll just write work energy, which is just that W is equal to delta K. It's basically the same thing. So basically, this is just kind of a trick question. So we know that torque is basically equal to force, right? That's its analog. So that means torque does work the same way force does, just rotationally. So again, they're just analogs. They have essentially the same function. And when something is analogous, they basically do the same thing, just in a different way of measuring, right? So something that you have to remember, like seriously, is rotational kinetic energy, again, is just equal to 1/2 moment of inertia times angular velocity squared. And also remember, rolling objects, they have two types. They have both translational kinetic energy and rotational kinetic energy. And remember, you use V is equal to angular velocity times radius to connect them. Remember that shape matters more than mass, which cancels out. And also remember that energy problems are not going to be the same as torque problems. Okay. And that's about it. Thanks for watching.